Hey everyone, and welcome. Today we're going to tackle a really fascinating repair job. We're bringing a completely unresponsive inverter back from the dead. Seriously, if you've ever had a key piece of tech just give up on you, well, you're going to want to see this.
So here's how we're going to crack this case. First, we'll get familiar with the victim, the dead inverter. Then we'll put on our detective hats and follow the voltage trail to find our culprit. After that, it's time for the revival operation, and stick around because at the end, we're going to uncover the secret of how one tiny little component took down the whole system.
All right, let's dive right in. Our case begins with a problem that I'm sure is all too familiar and incredibly frustrating for a lot of you. Just picture this for a second. The power goes out, plunging you into darkness. You walk over to your trusty backup inverter, flip the switch, and nothing. Not a light, not a beep, just absolute silence. It's a total brick. That's exactly the scenario we're facing here.
Now, in the world of electronics, this has a name. It's called a dead condition. Our patient today is a Luminous EcoWatt 900, and it's hooked up to a 12-volt supply, so we know for a fact power is available. But it's just not responding. The power's there, but the machine is completely out cold.
Okay, time for the investigation. Every good detective has to follow the evidence. And in electronics repair, that evidence is voltage. Our main tool for sniffing out the trail, the good old multimeter. The first steps here are just pure logic. Step 1, is power even getting into the inverter's main board? We check that? Yep. Okay, step 2, we start tracing that power toward the inverter's brain. That's the microcontroller, the little chip that runs the whole show. The goal is simple: find out exactly where that voltage trail stops. And boom, right away, we get our first big clue. We're seeing a nice, healthy 12.56 volts right at pin 1. That's the main entry point for the microcontroller's power circuit. And this tells us something huge. The power is making it all the way to the brain's front door. The problem has to be somewhere just beyond it. And this, my friends, is where the investigation gets really interesting. We've followed the trail, and it's led us to one single, tiny component that is about to become our #1 suspect. So, right before the power gets properly regulated for the microcontroller, it has to pass through this little guy, a tiny 1-ohm resistor. Think of its job as being like a miniature fuse or a little gatekeeper. It's there for protection. So we take our multimeter probe and we check the input side of this resistor. And what do we see? We've still got our full 12.56 volts. Power is flowing perfectly, right up to this exact spot. No problem here. And then, here it is, the aha moment. We move the probe to the other side of that exact same resistor, just a millimeter away, and the voltage drops to 0, a flat 0.00. The trail has gone completely cold. We've found the break. So what does this mean? It means the resistor is open. That's the technical term for it's toast. It's failed, it's burnt out, and it has created a total dead end in the circuit, completely stopping the flow of power. This one little component has single-handedly cut off the microcontroller from its life support. But the plot thickens. When a part like this fails, it can create a chain reaction. And a quick visual inspection shows us just that. 2 nearby capacitors, the components that store and release energy, are visibly swollen and bulged out. That's a classic sign of failure. So it looks like our resistor didn't go down alone.
Okay, the mystery is solved. We've identified our culprits. And now it's time for the best part. Let's scrub in for surgery and bring this machine back from the dead. The repair process is super methodical. First, just to be 100% sure, we do a quick test. We just touch a new resistor to the contacts for a second, and the inverter immediately beeps and lights up. Bingo! Diagnosis confirmed. So now we carefully desolder the bad resistor, get those 2 damaged capacitors out of there, and then we solder in the brand new parts.
So, the repair is done, the machine works, but the story isn't quite over. You gotta ask yourself, why? Why did one tiny, insignificant part cause such a complete, catastrophic failure? This is really the key takeaway from this whole thing. The source material had this just perfect analogy for what happened. It said the resistor was like a small but critical gatekeeper. When it failed, it was like the main gate to the city. The microcontroller was slammed shut and locked. All the power in the world could be waiting outside, but inside, the city was left in total darkness. And the numbers don't lie. Here's the proof. After the repair, pin 1 is still getting its 12.5 volts just like before.
But now, check out pin 20, which was dead, 0 volts before the fix. Now it's showing a perfect 5.0 volts. That confirms it. The microcontroller is finally getting the clean, regulated power it needs to wake up and do its job. The gate is officially open.
One final system check tells us everything we need to know. The inverter powers on with the normal beeps and lights. Check. The display works, showing a low battery message, which is exactly what it should do. Check. We test the charging circuit, and it's pulling a healthy 12 to 13 amps. Perfect. This thing is fully repaired, fully revived, and ready for action. And that really brings us to our final thought here. A single component, a part that costs maybe a few pennies, brought an entire machine to its knees. It really makes you think, doesn't it? What other tiny, seemingly insignificant gatekeepers are hiding in plain sight in all the complex systems we depend on every single day? Something to think about. Thanks for joining me on this one.